Hey guys, sorry I couldn't be there with you today. Because I'm not able to be there, instead of our usual format, I'm just gonna have you watch this video lesson as I walk through the note guide for lesson 3.4, which is gonna be covering intervals where, or finding intervals where a function f of x is concave up or down, and then learning about what's called the second derivative test. So first, I'm gonna have you start by connecting the ideas we learned in section 3.3 to the relationship between the second derivative and the first derivative of f of x. So the second derivative is the first derivative of the first derivative. So the relationship between f double prime and f prime is the same as that between f prime and f. So f double prime is the first derivative of f prime. When the first derivative of a function is positive, that means the function is increasing. So for the second derivative to be positive would mean the first derivative is increasing. For the second derivative to be negative would mean that the first derivative is decreasing. Because again, it's the same relationship between f double prime and f prime as that between f prime and f. And again, if f double prime is 0, that indicates a potential max or min value on the graph of f prime. Because, again, this is if the second derivative were to change signs. That would mean the first derivative of f prime would be changing direction, which means f prime would be hitting a max or a min. So this is basically the 3.3 lesson, but applied to the first derivative of f based on the second derivative of f. Okay, so then I want us to use that to start picturing what it looks like on the graph of f. What does it look like on the graph of f to have its first derivative increasing? So the graph of a function f that has an increasing first derivative, that could mean a number of things. That could either mean that, here's option 1. Let's suppose your function is increasing the whole time. So let's say f of x is increasing. Then for this first derivative to be increasing, f of x would have to be getting steeper and steeper and steeper. So we'd have to go from like small positive values of f prime, which is the slope of f, to large positive values of f prime. So f prime equals slope of f. So we would need gradual slopes moving into steeper slopes. That would be one way that f prime could increase. The other way that f prime could increase is if f itself were decreasing, but its slopes were increasing. So that would look something like this. This is if my original function is decreasing, but the slopes are increasing. Another way the slopes could increase is if they started off as like a really steep negative slope and then got flatter, like a less steep negative slope. So this would be going from a large negative slope to a smaller negative slope. Well, as we know numerically, the smaller the negative, the greater the value. So smaller negative equals greater value. So to go from a large negative to a small negative meaning like the function's going down but flattening out, like going from a steep negative to a flat negative. That would mean that the slopes themselves are increasing in value since their negativeness is getting less. And then the last option is if I kind of put all this together. So if a function started out going down and ended going up, that would also be the shape of something that has a first derivative that's increasing. Because again, over here on the left side, you can see that it has like a really steep negative slope. And as I continue moving from left to right, which is what we're always doing when we're looking at increasing, decreasing, we always move from left to right. As I do that along this curve, I notice that my negative slopes get smaller or less negative, and eventually hit 0, which technically is greater in value than negative, and then become positive and eventually more and more positive. So a curve that looks like this has slopes that start as steep negatives and end as steep positives. So that is a depiction of what's happening when your slope, aka your first derivative, is increasing. So then the question is, what would it look like if the first derivative values are decreasing? So now your slopes are going down in value. Well, option 1 would be if your original function is going up, but the slopes are getting smaller. That would have to look something like this. So if your function f of x is going up, it would have to be getting flatter as you go up in order for its slope value to decrease. So for the slope value to decrease, we would want to go from steep positive slopes to flat or less steep positive slopes. That would mean that the slope values are decreasing. So this is one visual image of that. Another visual image of a first derivative decreasing would be if the function itself was going down. So going down, but with decreasing slope values would mean a flat negative slope becoming a very steep negative slope. So like a smaller negative becoming a larger negative. So relatively flat negative slope becoming a very steep negative slope. So that's what it looks like visually if you have a function f of x that's going down and its slope values are also decreasing. That would be something that gets steeper and steeper and steeper in the negative direction. So we've got flat negatives becoming steep negatives. That would mean slope values are decreasing. Okay, so that's what it looks like if a function is either increasing or decreasing. If I were to put that together and have a function that does both increase and decrease, that would be option 3. That would mean a function could go from a steep positive to a flat positive, and then from a flat negative to a steep negative. It would have to look something like this and go all the way from those steep positives, pass through 0, and end at a steep negative. So it could go from steep positives to steep negatives. That's again steep positive slopes to steep negative slopes. And that again would be what it looks like when your first derivative is decreasing. Okay, so what are we noticing here? What we're noticing here is that if my first derivative is increasing, that of course would be when my second derivative is positive, I have shapes that look like they're opening upward, right? We would call this concave up. And that's the shape that's formed if you have a first derivative that's getting greater in value. So flat positive getting steep, or steep negative getting flat, or steep negative ending in a steep positive. These all create shapes of f of x that would be concaving up, opening upward, like an upward facing parabola. When the first derivative is decreasing, however, which would be when the second derivative is negative, so that's going to create images that are concaving downward. These are like opening downward, like a downward facing parabola, or one side or the other of a downward facing parabola. That's because the slopes are having to either go from steep positives to flat positives, or from flat negatives to steep negatives, or from steep positives to steep negatives. All of these create shapes that are what we call concave down. So the sign of the second derivative tells us the concavity of the very original function. So if the second derivative is positive, that means the first derivative is increasing. That means the original function is concave up. And then conversely, if the second derivative is negative, less than 0, that would cause the first derivative, slopes of f, to decrease, which would cause f of x itself to be concaving downward. And so that's the big main connection in 3-4, is this connection between the sign of the second derivative and the concavity of the original function. So then that will lend itself to the second derivative test. So now what I want you to consider is then, okay, let's say I have a graph of a function that has a positive second derivative. So that means the function itself will have to concave up at a specific value for c. So at a specific value for c, the graph would have to either be going like this or all the way, right? And then also at that specific value for c, at that point, the first derivative, the slope of f, is 0. So that would have to be something like this, and c would be right here. The function would have to be concaving upward with a horizontal tangent line, or a 0 slope at c. That would cause the function to be hitting a relative minimum at c, just because of the concavity of the graph and the fact that it's hitting like a turning point. It's hitting a max or a min. Well, it would have to be a min if the function has a positive second derivative, causing f of x to be concave up. And then over here, if the function has a negative second derivative, which is causing the graph of f to be concave down at c, right? That's what it means to have this c plugged in here. And if the first derivative is 0 at c, causing the graph to have to flatten out, right? You have to have a flat part on your graph if your first derivative is 0. That would have to look something like this. Concaving down with a flat tangent line right at the x value of c. Well, the only way that could happen is if the function is approaching a maximum value, or reaching a maximum value at x equals c. So that's what we call the second derivative test, when you use the second derivative in combination with the first derivative to determine whether or not f of x is reaching a max or a min. So here, if my first derivative is 0, right, so that means it's a potential max or min, and my second derivative is positive, making f concave up, that would tell me for sure that f of c is a relative minimum, because it would be basically at the bottom of a concave up shape. And then similarly, if the first derivative is 0 and then you test the sign of the second derivative at c and find that the second derivative is negative, that would tell us that f of c is a relative maximum, because it would be sitting at the top of a concave down curve. So lastly, if the second derivative itself is 0, so we haven't quite talked about that, but we should talk about that now. If the second derivative is 0, that would mean there is a sign change, or sorry, and there is a sign change on the second derivative at c. Then that would tell us that f prime of x is changing direction at that c value, and that would tell us that f of x is changing concavity at that point, and has what we call a point of inflection at c. So a point of inflection would be a point where the second derivative is not only 0, but also is changing sign. So remember, just because a derivative or second derivative is 0 doesn't necessarily mean for sure that they're going to change sign, but if they are going to change sign, it would have to be at a point where they're 0. So this section is going to also want us to find points of inflection, which are specifically points where the second derivative is changing sign. Okay, so let's go ahead and walk through the examples on the note guide. So for the first example, it just wants us to determine intervals. It just wants us to find intervals where the function is concave up or concave down, and then we'll confirm it with Desmos. But concave up basically are going to be intervals where the second derivative is positive. Concave down is going to be intervals where the second derivative is negative. So we're basically going to have to find, first of all, the zeros of the second derivative, and places where the second derivative might not exist, because that would be where the second derivative changes sign. So first, I'm going to find the first derivative, because you got to find the first derivative in order to find the second derivative. To do that, I'm going to have to use the quotient rule. So I'll think of my x squared plus 1 as u and my x squared minus 4 as v. And then I'm going to have to do a u prime v minus v prime u over v squared derivative. So my u prime would just be 2x multiplied to v, that's x squared minus 4. My v prime would also be 2x multiplied to u, that's x squared plus 1. And all of that is over x squared minus 4 squared. So I'm going to go ahead and simplify in the numerator a little bit and then take the second derivative. So in the numerator, I'm going to distribute the 2x. And then I'll do that over here too with the negative as well. And then I know that this is all divided by x squared minus 4 squared, but for right now, I'm just going to simplify my numerator. I notice that the 2x cubes cancel out, and then I can go ahead and combine these terms, the negative 8x and the negative 2x. Sorry, this is the first derivative, not the second derivative. So I end up with negative 10x, and then it's all being divided by x squared minus 4 squared. So that's my first derivative, and I'm going to just skip right on past that because this isn't asking me for max or minimums. It's asking me for intervals of concavity. So for that, I'm just going to go straight to the second derivative. And that requires me, again, to use a quotient rule. So u will be my negative 10x, and then v will be my quantity x squared minus 4 squared. So u prime, that's just going to be negative 10 times v, that's just going to be x squared minus 4 squared. V prime is going to require the use of the chain rule and the power rule, 2 times x squared minus 4 to the first times 2x, and then times the negative 10x, which was u. So this whole part is v prime and then times u, and then all of that is over v squared. So x squared minus 4 squared squared, or to the 4th power. Okay, so now I need to simplify the numerator of this function. That'll make it a lot easier to find what makes it 0. So what I'm noticing is that I have a common factor of x squared minus 4 across these two terms. So like this is one part of it, and then this is the other part, because these are the two parts separated by subtraction. Maybe I'll simplify over here. I'll go ahead and multiply the 2 and the 2x and the negative 10x first before I attempt this factoring. So let me just write this again as negative 10 times x squared minus 4 squared minus, and then I have 2 times 2x times negative 10. So that would be 4x times negative 10x. That would be negative 40x squared. And then all of that times x squared minus 4. And then because I have a negative times a negative, actually those will become positive. Okay, so what I have in the numerator is this expression. So I'm going to go back to recognizing that I have a common factor of x squared minus 4 in both of these sections, this part and this part, and I will factor that out. I will factor out the x squared minus 4 from this term and this term. And then I'll put the leftover stuff in here. So when I take out an x squared minus 4 from here, well, I had 2 factors to begin with, so I'll have one more factor of x squared minus 4, and then also this factor of negative 10, plus when I take x squared minus 4 out of this part, I'm just left with the 40x squared. And then all of that is being divided by x squared minus 4 to the 4th power. So now I'll simplify in my numerator a little bit. I can distribute my negative 10 to the x squared and the negative 4, and then I can combine the 40x squared with the negative 10x squared that I'm going to get when I distribute. So then in my numerator, I will have x squared minus 4 times 30x squared. Again, that's from the negative 10x squared plus 40x squared, and then plus 40. 30x squared plus 40. And then all of that is over x squared minus 4 to the 4th. And then I can cancel out one of the factors of x squared minus 4. Okay, so I'm going to use this simplified version of my second derivative to determine where this second derivative either equals 0 or is undefined. So we had done this back in 3.3. If I want to find where the second derivative equals 0, I would have to just take the numerator and see if there are values of x that make the numerator 0. If so, that would be where the second derivative equals 0. So what you might notice, though, is that this has no real solution because the x is being squared. So even if x were negative, the x squared becomes positive, and then I'm adding these together. So it's not going to become 0. The other way you could think about it is subtract 40 to the other side and then divide by 30. And you'll notice that you're getting an x squared equal to a negative. So there's no real number solution to that equation, which means there's no point on our graph, so to speak, where my second derivative, there's no point that would show up on our graph where my second derivative is 0. So this one doesn't have any points where the second derivative is 0. But if I look at the denominator, it does have places where the second derivative doesn't exist. So I have x squared minus 4 to the 3rd power, although it doesn't matter how many powers of it I have. If x squared ends up equaling 4, then this becomes 0, and 0 to the 3rd power is 0. So then I can't let x be, or yeah, in a sense, I can't let x be positive or negative 2, because if I did, that would make the denominator of my second derivative 0, which would make the second derivative not exist. So this is finding places where second derivative doesn't exist. And those are still potential places where the second derivative might change sign, which is what we're really trying to find. Is there a place across this graph where the second derivative changes sign? And it looks like there are places at positive or negative 2. Now, if I go back to the original equation, which is this right here, I can see that the domain for that includes all real numbers except 2 and negative 2. So those aren't even part of the domain for this function. However, I'm still going to use those as potential changes in concavity, because even if like you have an asymptote, for example, like a vertical asymptote on a graph, the concavity on one side could be concave up where the other side is concave down. So even a place where a function doesn't exist could still indicate a change in concavity and give me endpoints for intervals for graphs going concave up and concave down. So I still use those type of points in my sign charts. So I'm going to set up a sign chart going from negative infinity to negative 2, then from negative 2 to 2, and then from 2 to infinity. And I'm just checking the sign of the second derivative. And then that will help me determine the concavity of f. So I'm going to test something to the left of negative 2, so maybe like negative 3, and I'm just going to look at my second derivative to decide the sign, right? So if I were to plug in something like negative 3, my numerator is going to be positive no matter what, and then my denominator would also be positive because I'd have like 9 squared minus 4, which is positive. So on that section of the x-axis, my second derivative is positive, which means my original function is concaving up. And then from negative 2 to 2, maybe I'll test like where x is 0. So then I'd have 40 over like a negative number cubed, which is negative. So that'll give me a negative sign for my second derivative, which means my concavity for f of x would be concave down. And then on the right side of 2, say 3, I'd plug 3 in here. I'm going to have a positive, again, divided by a positive. Because again, I'd have like 9 minus 4, which is positive. Okay, so I can tell that the concavity does change across these x's of negative 2 and 2, even though there are points where the original function doesn't exist. So my final answer for this, I would say f of x is concave up on the intervals from negative infinity to negative 2, and also from 2 to infinity. That's where my graph is concave up. And then it's concave down on that in-between interval. So from -2 to 2. So that would be our final answer for that one, since it was asking us to tell intervals where the function's concave up or concave down. So to recap, basically what I had to do, I had to first find the first derivative, and then take the derivative of that to find the second derivative, which was all of this part. I then had to find places where the second derivative was either equal to 0 or where it didn't exist. So that was what these two things were looking for. The only points I found were positive and -2. The second derivative didn't exist there. The original function didn't even exist there. But what we're learning here is that places where a function doesn't exist could still be indications where concavity of a function is changing, or the sign of the second derivative is changing. So I noticed that there are these 3 different intervals, each having a different concavity from one interval to the next. So that's how we find our intervals. Now what I want us to do is just check this with the graph of this function to see if what our sign chart told us was accurate. Okay, so looking at the graph of this function here on Desmos, I can see that my sign chart was right. So on the left of -2, and by the way, this function has a vertical asymptote at -2, and another one at +2. So the function itself did not even exist. But to the left of that vertical asymptote, I can see my function has this concave up shape. In between the vertical asymptotes, it has this concave down shape. And then on the right side of that vertical asymptote, it's concave up. So the sign chart was able to give us an idea of the concavity, actually a complete picture of the concavity of this graph. Okay, so in example 2, again, we're being asked to find intervals where a function is concave up or concave down, but this also wants us to find x values where our function might have a point of inflection. So again, a point of inflection is any point where f double prime changes sign. So that could happen at a point where it's 0 or at a point where it's undefined. So, and then we're also going to determine x values for the extreme value on the graph of x, and we'll confirm this with the graphing device. So we're going to use both our first and second derivatives for this one. But on my way to the second derivative, I have to, of course, stop at the first derivative. So I'll start by taking the first derivative of this using the chain rule. So it's e to a power. The derivative of that is e to that power. And then I'd have to multiply by the derivative of the power. So it would be, I would multiply the 2 to the -1/2, which would just be -1, and then subtract 1 from the power. So negative x, essentially. So this is just negative x times e to the negative x squared over 2. So that's the first derivative, which we'll come back to later when we're looking for extreme values. But right now, I'm going to just first look for intervals of concavity and points of inflection, so I need the second derivative. To do the second derivative, though, I'm going to have to use the product rule because I've got u, which is just y equals negative x, and then v, which is e to the negative x squared over 2. And I'll have to do u prime v plus v prime u, product rule. Okay, so u prime is just -1. V is, of course, e to the negative x squared over 2, plus v prime, which is just this again, because our original function was v, essentially, so this whole thing is v prime. So negative x times e to the negative x squared over 2, and then times u, which is negative x. So now I have negative e to the negative x squared over 2, plus these two negative x's multiply together and just become x squared times e to the negative x squared over 2. And then I'm going to simplify that a little bit more by just factoring out the e to the negative x squared over 2. And don't forget there's like this -1 in front being added to x squared. Okay, so to find my points of inflection, which would be where second derivative changes sign, and also determine intervals of concavity, I'm going to need to figure out where this second derivative is equal to 0. There are no points where it's undefined because e to whatever power is defined all the time, and then polynomials are defined all the time. So the domain for this is all real numbers. So that's not a thing. But there are places where it's going to be 0. This part, the e to the negative x squared over 2, that'll always be greater than 0. So it's never going to equal 0. So we don't really worry about that factor. It's this part, the -1 plus x squared, that part could equal 0. So you could think of it either as like a difference of squares that factors into x plus 1, x minus 1, or you could think of it as like add 1 to the other side, square root both sides. At any rate, you get -1 and +1 as your possible places where the concavity might change on the graph of f. So these are our zeros of the second derivative. Yeah, okay. So then I'm going to do a sign chart with those values, and the domain of the original function f of x is also all real numbers. So I'm going to split up your entire number line that goes all the way from -infinity to infinity across these points of -1 and 1. So that creates 3 intervals, if you will. So I'll start with -infinity to -1, 1 to 1, and then 1 to infinity. These are my 3 intervals, and I'm just checking the sign of f double prime, excuse me, at each of those intervals. So to the left of -1, maybe I could plug in, say, -2. I'm plugging it into here. Well, no matter what I plug into this equation, the answer will be positive. So this is positive times, and then if I plugged in a -2 and squared it and added -1, that would be positive. So positive times a positive is positive. So my function is concaving up for all x's less than -1. Between 1 and 1, so where x is 0, so if I plugged in 0 here, I still have a positive. If I plug in 0 here, I'd have a negative. So positive times a negative is a negative. My original function f of x would be concaving down. And then if I plugged in something to the right of 1, say 2, again, I'd have a positive here times a negative, or no, times a positive, sorry. 2 squared minus 1, that's positive. So I would be concaving up again on that far right interval. Okay, so I can say part of my answer already. I know that there are points of inflection. Sorry, this should say -1. There are points of inflection at -1 and 1 because my second derivative does in fact change sign here and here. So I'll write that as part of my answer. So I know that, and then I can say also that f of x is concave up for all x's between -infinity and -1, in addition to all x's greater than 1. And then it's concave down for all of the x's in between -1 and 1. So I answered the first part of this question. The second part of this question is wanting to know about the x values. So we're just going to find the x values for any extreme values on the graph of f. So what I'm going to use in addition to the concavity of f is I'm going to use the zeros of the first derivative, sorry. So this here was our first derivative. And so what I need to do is go back to that. Maybe I'll use red down here again. So my first derivative was -x times e to the -x squared over 2. I need to figure out where that is 0. Because again, this is going to be defined for all real numbers, so there are no places where it's undefined, but there are places where it could equal 0, and that would specifically be when x is 0. Because e to the -x squared over 2, like this part is never going to be 0. So we just need to worry about like this factor being 0, and that would happen when x is 0. So the only potential max or min value for f of x would be when its first derivative is 0, which is when x is 0. So now what I have to do is go over to my concavity chart and notice that when x is 0, that was in between -1 and 1, the concavity of f is concave down because the second derivative was negative. So at x equals 0, we can say that f prime of 0 is 0, and f double prime of 0 is negative. So it's like it's one of these situations. So what that tells me is that f of x has a relative max at x equals 0. And since this question only asked us if we were to find locations of relative maxes, we are not being necessarily asked to decide if it's absolute versus relative. So I don't need to do any further examination with like the first derivative. We can just end this question here. We know that it has a relative max at x equals 0. Okay, and then with our last example, we're going to be looking at this equation here. We're finding values where f of x has a point of inflection. We're looking for intervals of concave up, concave down, and we're just locating the relative extreme values. And then we'll confirm with a graphing device at the end. So again, to figure out points of inflection, that would be where the second derivative changes sign. So we have to find the second derivative and see where it's equal to 0. So of course, to find the second derivative, we have to first find the first derivative. So the first derivative would be negative 15x to the fourth and then plus 15x squared. We'll come back to that later. The second derivative would be negative 60x cubed plus 30x. So this is the one that we need to find the zeros of. I don't need to worry about it being undefined because it's a polynomial. So it's defined for all real numbers. So I'm going to factor out a negative 30x, and I'm left with x squared minus 1 equals 0. No, sorry, 2x squared. 60 divided by 30 is 2. I can do this. So that's 2x squared minus 1. Okay, so over here, I end up with a possible 0 if x is 0. It's actually really more related to the x part. The negative 30 doesn't really matter. But if x is 0, then all of this turns into 0. The other thing that could make the second derivative equal to 0 is if 2x squared minus 1 is 0, which would be where 2x squared equals 1, which would be where x squared is equal to plus or minus rad 1/2. Okay, so I have these ugly numbers, but it's okay. Sorry, I already square rooted. It's x squared equals 1 over 2, and then x equals plus or minus square root 1 over 2. There we go. So these are my potential places where I have a point of inflection. So I'm going to set up my sign chart across these numbers. Notice my domain for f of x is all real numbers. So that means the whole entire number line. So we're going from negative infinity to infinity. I've got a negative rad 1/2 and then a positive rad 1/2. Oh, and 0. And 0, don't forget this guy over here. So 3 places where concavity might change. So that's going to give me 1, 2, 3, and then 4 intervals. So we'll do negative infinity to negative rad 1/2. And then negative rad 1/2 to 0, 0 to rad 1/2, and then rad 1/2 to infinity. So that's my split up x-axis. I'm going to look at the sign of the second derivative. So to the left of negative rad 1/2, maybe I could do something obvious. Like I know negative 1 is going to be more negative than negative rad 1/2 would be. And I'm testing the sign of my second derivative. So if I plug negative 1 in here, that would make this first part positive and the second part positive as well. So my second derivative is positive for my first interval. So then that would make my function concave up. And then between negative rad 1/2 and 0, maybe I could do something like negative 0.1, because that would be a really small decimal, smaller than negative rad 1/2. So if I plug negative 0.1 in here, I'd have a positive. And then, so this, okay, so imagine I'm plugging in like a super small number, like negative, maybe I'll make this negative 0.01, just to make it super obvious, which is like 1 over 100. So imagine I have 2 times 1 over 100 squared. That would be like a really, really small number, minus 1. That's going to be negative. So if I plug in this negative, I have a positive times a negative, I get a negative. So my function is concaving down because its second derivative is negative. Over here, maybe I'll imagine plugging in a positive, really, really small decimal, 1 over 100. That would make this negative. That would also make this negative. so that a negative times a negative is a positive. So my original function's concaving up. And then something greater than the square root of 1/2 could be like 10. Nice, easy number to imagine. So that would make this a negative, and then that would make that a positive. Negative times a positive is a negative. So my function is concaving down. Okay, so I see that I have 3 points of inflection. I have one here at this negative square root of 1/2 because concavity changed. I also have a change in concavity at 0 and then another change at rad 1/2. So those are my 3 points of inflection. I'll just say 0 and then plus or minus square root 1/2. And we know that f of x is concave up on the intervals from negative infinity to negative rad 1/2 and 0 to positive rad 1/2. That would be where the function's concave up. The function is then concave down on the other two intervals. So we answered the first part of this question, which was wanting us to state where f of x has points of inflection. We did that. Find intervals of concavity. We did that. Now we just have to figure out relative extreme values. So actually here when it says relative extreme values, those are the y-coordinates of our maxes and mins. So we're going to have to plug things back into this original equation for this last part. But before we do that, we have to revisit our first derivative over here, this guy. We have to find zeros of the first derivative. Okay, so to solve this one, I'd have to factor out a negative 15x squared, and that will leave me with positive x squared and then minus 1. So I noticed that I have a place here where at 0, right? If x is 0, then x squared is 0, then this whole thing's 0. But also if x squared minus 1 is 0, which would be when x squared is 1, which would be when x is plus or minus 1. So these are my potential locations of a max or a min. So maybe we'll start with the x equals 0. So notice that f prime of 0 is 0, but f double prime of 0 is also 0. That means that at x equals 0, there is neither a max or a min. It's not a turning point. And if we were to do a sign chart for f prime, which I'm not going to do here, we would notice that this derivative doesn't change sign across this 0. So the function is not reaching a max or min, it's just flattening out. It could look something like this, where it flattens, but then it keeps going up, something like that, or it could be going the other way around. At any rate, it's not hitting a max or min, it's a point of inflection is what's happening. It's a point of inflection. We mentioned that earlier, right? It has a point of inflection at 0. So neither a max or a min, just a point of inflection. Something kind of like that or that. Okay, so the only max or mins are going to be at 1 or negative 1. So what we need to notice is that, so f prime of 1 is 0. F double prime of 1, according to this sign chart, so that would be like in this interval. So that would be in this interval over here. That is where my second derivative is negative. So the f double prime is negative. So that would be like a concave down situation, causing this 0 derivative to be locating a maximum. So we have a relative maximum at x equals 1, and it asked us to actually find that maximum value. And so we'd have to actually plug that into the very original equation because it said find the extreme values, not the location. So I'd have to plug 1 in here, and I'd get negative 3 times 1 plus 5 times 1. So basically 2. I'll just write that. Negative 3 plus 5 is 2. So 2 is a relative maximum value on this graph. Then if I look at my negative 1, so f prime of negative 1 is 0. F double prime of negative 1 over here is going to be part of this interval. Negative 1 is in here. So f double prime of that is positive, greater than 0. So that would mean that f of x is concaving upward. which would cause that zero slope to be hanging on the bottom of it, causing it to be a relative minimum. So f of x has a relative minimum value at x equals -1, and then the value of that minimum would be what I get when I plug -1 into the original equation, which is up here. So -3 times -1, that's +3, plus 5 times -1, that's -5. That would give me -2. So I have a relative minimum at x equals -1, and the minimum value is -2. And that's all that we needed to answer for this one. It doesn't tell us to decide if they're absolutes or not, so we don't need to look at the sign chart of f prime. We just needed to find the values of these relative maximums. And so that answered the last part of this question. So we've finished the note guide for 3-4, but I'm pretty sure you have some time right now in this block period, period 5. And so I want you to also begin working on the practice questions from your textbook. The pages are scanned and posted in Canvas, so I want you to work on those now so that you have this assignment completed on Monday, by Monday. Actually, no, I take it back, before Monday, okay? So use your time right now. I'll be back in school tomorrow. Please feel free to swing by if you have any questions, and I will see you then. Bye.